This is called regenerative circuit. The way it works is this return line is not connected to any of the return port of the four-way directional valve. Instead, it is connected right after the pump. So whatever the pump is producing, imagine that pump is producing here QP amount of flow. And then this return line is the flow is coming QR from that. So instead of dumping to the reservoir, like in the earlier cases we have seen, we don't dump the return flow in the reservoir. Instead, we connect right after the pump. So what happened? It adds the flow. So the total flow would be QT is, we can write the QP plus Q regenerative. So that is the total flow for the regenerative circuit. So when we set up like this, so during the extension stroke, the regenerative circuit, the total flow is QP plus QR. So to calculate pump flow, we can solve for pump. QP is equal to QT minus QR. QT. Now, remember, we are developing all these equations for extension stroke. We are thinking that the cylinder is extending now. So going this way, going out, and the velocity of extension is that. So QT, total flow that coming this way, that's the QT. So we can write QT is equal to the area of the piston, the area of the blanket like this area, times the velocity of extension, EXT, minus then the regenerative flow or return flow. We can calculate the area of the rod end, which is the area of the piston minus area of the rod. So that is the amount of fluid I have, cross-sectional area, times the velocity of extension to get the now if we just, so this one cancel, I will have AR times velocity of extension, so that's QP. Now if we calculate velocity of extension, that's gonna be equal to QP pump flow divided by the rod area. Now piston area is larger than the rod area. So as you can see here, the velocity of extension increases in the regenerative flow. However, the power does not increase. Now in a regenerative circuit, because it's connected here, the return line is connected right after the pump. If we ignore the losses in the four-way directional valve, then we'll have basically same pressure on this side and also on the blank side. So the blank side and also the rod side will have the same pressure. If we have the same pressure both sides, so we can calculate the blank end force like this. FV is equal to pressure times the area of the blank end, and then which is area of the piston. So P times area of the piston. And then the rod end force, we can calculate pressure times the rod end area, which is area of the piston minus area of the rod. So now whatever left, that will be the force carrying capacity. So F load, this system can take the load FB minus FR. So we increase the velocity, but the force kind of decreases proportionally. So if we do this calculation, F load will be, let's put all these values. So PAP minus then pressure times AP minus AR. So resultant, I will have PAR. So that is the load. As you can see, the load significantly decreased because the area of the cross section of the rod is smaller. So velocity increases, force carrying capacity decreases. Then we know that power is equal to force times velocity. So that is the power. So if velocity increases, then force decreases. So power is basically kind of constant, because the pump power, whatever the pump is producing, the hydraulic power, so we can say power produced by the pump, which is PQ by 1714, that is kind of fixed. That is the power of the pump. So we cannot, just by increasing the velocity, we cannot really get more power. Then the force carrying capacity decreases and vice versa. So that's one of the advantages of regenerative circuit. We can increase the velocity and then carry smaller load, or the vice versa.